And as you guys can remember, we begin to talk about regressions, and as I mentioned several times, it will be the first topic in the machine learnings. And what is the regression is, I mean, you all of you guys, you already know regression is given some data points will be the best fit. So it's approximation problems. You can have the curved fittings, and you might have straight lines. So I'm not saying which one is good. I'm saying this straight line is the simplest one. So that's why I'm going to start with linear regression. So because I mean, I'm not saying linear regression is good. I'm saying linear regression is simple enough so you can get started with that, the linear regressions, to get the insight or ideas of regression problems. So remember that for regressions, the data points that we need to supposed to have is that we need to have input and outputs at the same time. Those are the paired data set, and we need multiple of them. I guess in the example that I use as my 13 data points, you can have 100 or 1,000 or million data points. But remember that in order to utilize the the regression model, in order to build the regression models, you need to have input and associate or corresponding outputs at the same time. That's a paired data set. We call it in machine learnings or AIs, it's a supervised learnings. Input and outputs at the same time. That's the data, the required data informations for generally, I would say, for supervised learnings. And what I did is that given the linear regression problems, transfer it to the optimization problems, right? That's where we here X and Y data points, I put them in the column vector. I put them in the column vector. Actually, this is vector. Okay, and this is measured or observed outputs. We assume that that's true values. What we want to do is that we want to get, or we want to predict true values out of input informations, which is over there. Of course, we're not going to get exact values, so that's why we want to have best approximations. It turns out to be optimized. That's why we have optimization problems. We want to minimize these, right? That's actually true values or actual values or ground truth. And this is the predicted values out of input information. And Y hat, there are many ways, and probably I would say this is the generic expressions. The output X of predicted value is going to be the function of inputs, right? But again, the simplest one is probably the linear models. That's why I have that one, like the constant or the first, or the here is as the first degree of polynomials. And these two unknown parameters is gonna be the decision variables in the optimization problem. So there's some trick that I said that here, and this is the linear models that I assume that, and you say that's like one in front of it, and you can have the reason that I want to everything given data points, I want to have them in a matrix or vector form so that we can do matrix multiplications. And we do have y1, actually y1 hat is, right? And y2 we can do that with for all given data points. And we can combine them that's the trick that I want to see. All right. And again, here it looks like it's a matrix and vector multiplications, and it turns out that it's column vector. Then this is y vectors, y hat. So I want to have, this is given data points, I mean vectors, and y hat vectors. I want to minimize it. I'm going to find out the theta naught and theta 1 such that minimize in, probably I would say in 2-norm distance. So that's why we know that for that case, again, I mentioned that this A and B, this is the notation that we learn in, but here in linear regressions, I changed the notations. And we know that the solution is like that. I did several times. So we can find out the solutions. That means we can draw. We know that slope, and at this point, so we can draw the straight line out of predicted linear regression model. And there's some side note over there. Given inputs, I mean, this is tricky part, and I add 1. I mean, that's not the additional information. So the amount of information that we have from here and here are the same, because just trivial, I just add 1. And out of these features, I want to predict y of hat. And this is the like A theta, or you, I mean, okay, we used that one, this notation before, or B. Now I want to have, I mean, these A is different. I would say theta or Y. Okay, I just change the notations. And remember, in order to get theta naught and theta 1, there's some, these gonna be 2 column vectors like that. And if you do multiplications, then we can have different values of thetas. That means these gonna be any vectors in the spanned space spanned by these 2 column vectors like that. You can visualize it. I hope you guys can visualize in m-dimensional space. M-dimensional space. In n-dimensional space, you have 2 column vectors like that, and there's some coefficient, so you can span it. And in m-dimensional space, you have b vectors like that. Most likely, it's going to be out of that plane. So do the projections on top of it. That would be the best approximations. So use these illustrations to visualize in your mind. Even though this is the visualization in 2 or 3D space, I hope that you guys are able to visualize or imagine in m-dimensional space. Another way that or you guys can think of, or you guys are supposed to think, is that again, this is least square problems. You guys can compute the gradient. I mean, you can get exact solutions. You reach the same solutions like that. I mean, it really is up to you guys. You guys, if you love to think about in geometric interpolations, this one might be easier or better for you guys, or you love to like calculus or derivatives, whatever, and you guys can do in that way as well. It doesn't matter. Only thing that you at the end, you end up having the same solution, so it doesn't matter. So that's, now let's go back to the linear regression problems. And there are several ways that we can find out the solutions. And the first thing is, we already know solutions out of projections, either projections or least squares. So we know that this is the solution that I have. Suppose we have certain data points like that. So this is X and this is Y. And I remember in the previous slide, I said that I want to put everything in certain data in column vectors. So that's why we have reshape command here. So it looks like these are like this way, but we had a reshape function, so I made it in the vertical or column vectors. So I define X and Y, and I plot it. I mean, whenever you have data, the first thing you need to do is visualize it or plot it to see some kind of ideas and what's going on among the data points. So plot is the first step for data scientists. Remember that. And again, for I'm not going to go in details, but see, here is the shape. So I get the M is 13, and we have A matrix is like, remember, in 1 and X of 1, X of 2, right? So one thing that we can do is that we have two column vectors like this, and we have stack command, but we stack it in horizontal way. So we have an H stack. So we have all ones with the shape of this and X. So we can build up the A matrix. This is the one way that we can do. The second way is that, I mean, there's trick. This is the X, but we have like that. So whenever you have, it's going to be 1. This kind of trick that I love to use very often. So we build up the A matrix, and here up to A is in kind of, and we define it in NumPy. And I want to do matrix multiplications and whatever matrix operations. So I convert it into S matrix. Now that we can use that here, A dot T, which is A transpose, multiply by A and do inverse and A transpose and Y. We can calculate, we can compute theta. Right? I mean, here as a matrix is not like, in computational wise, it's not efficient, but here this is, I want to show you these the mathematical equations and the codings are very like intuitive and similar. That's the only reason that I use as a matrix command. But suppose you build up some kind of systems, but this requires extra computation, so there's no need to do that. In that case, you have to do matrix kind of operations in NumPy, right? And the last thing, once we get the values of theta naught and theta 1, all you need is just plot it. And then you can see, I I mean, your linear regression model is, I think it looks decent. And pretty much, I think it's a pretty good, it did a good job. But remember it, this one is, the dimension is X and Y. We have one value for the input, one value for the outputs. And that's the simplest case that you guys can think of. In say, in general case, you said we have 10-dimensional space. You cannot visualize it, you cannot plot it. That means out of the data points, you're gonna build up some kind of linear regression model state. There's no way that you can plot it to see whether your model is adequate or not. That's the kind of the challenging point or difficulties in that. Imagine you have something out of your whatever method that you used, and if you are not sure about whether your model is good or not, so you should have some kind of validation step. The easiest way is if you can visualize it, that's the easiest one and very intuitive. Everybody can see and can agree that your model is good. But in most cases, in general case, there's no such thing that you can do. If you have in higher dimensions in general. And second, okay, let's go back to the original problem that we have. The second way is we can also, it's convex problem. It's a convex problem, so we can use iterative ways, which is the only thing that I discuss in this lecture is gradient descent. And this is a f objective function, so we can compute the gradient and repeat. Remember that this is a formulation for gradient descent, and I think I already did that so compute the gradient and update it theta and do multiple iterations. I mean, again, this is just the example that I want to show you. This 1,000 values. I mean, it doesn't mean anything. You can just try like 10 times or 100 times, or you can put another like stopping criteria. I guess in that case, it's much smarter than this. And I guess another way that you can do is they use a CVXPY. Remember that and capitalize it. And I'm not sure which one is adequate for in case the version that you have in Colab. I'm not sure which one is, but try everything and figure it out which one is right for you guys. And two norms and a theta minus y, era theta, a times theta minus y. This, I mean, the biggest advantage, or that's the only reason that I introduced CVXPY. CVXPY is not a common optimization solver. It's very unique, but that's the only reason that I said once you build up the mathematical expressions and models, extremely intuitive. That's the only reason that I'm using this introduce CVXPY in this lecture. All right, so I show you 3 different ways they compute the linear regression models and to get the solutions. Just, I guess everybody is happy about it. This and at this moment, and let me ask here, remember that given data points, if that's the linear regression models, what actually did is that, say this is the distance. Suppose we have only 3 data points, that means squared that's the definition of two norm. But I think I mentioned so many times the distance, we do have multiple definitions. I mean, so this is the definition that I use that for this case, but we can do we can try this one as well. I mean, the first norm, this is same as like this. So the only difference is that here I want to minimize discrepancy or errors in terms of two norms. That's what we did so far. And I'm thinking that there's no specific reason that we have to stick with the two norms. So let's try one norm like this. Let's try that. I mean, there's no specific reasons that we can use one norm or two norms. It doesn't matter. So let's try, see if what kind of get the outcome that we can result that we can get out of it. So do we have to use only two norms? No. Let's try one norm. In that case, how do you compute it? Probably it's not easy, but the CVXPY, the only difference, that's the only difference. And this is the only reason that I want to use a CVXPY in this lecture. And how to compute it? Don't worry about it. Forget about it. Hope that the CVXPY can compute and get the solutions, give us the right solutions. Don't worry about what's going to happen behind the CVXPY. And I guess the value itself is pretty much, I mean, of course it's different, but I don't see the big difference. So let's plot them. Bingo. So two norms and one norm also provide the decent linear approximations, which is good. Okay, now you guys, the lesson that you guys can learn it. Okay, there are many different definitions of distance, and in many cases, it doesn't matter and give us very similar result. Right, that's the first lesson that I want you guys keep in your guys' mind. Then let's move on to another kind of experiment. What if outlier exists? What is outlier? What's the definition of outliers? And let me show you. So here, the data points are the same as the previous one, 13 data points. And I intentionally add 2 extra data points, which is outlier. I mean, it's totally like has nothing to do other than the previous data points. And probably say now we're starting from 13 data points, now add 2 more data points. So in that case, probably you guys can think like these data points, but somehow we don't know, like it's mistakes by like humans, or there's some kind of the system that dealing with has the characteristics are changing, whatever, any kind of reasons. These are the 2 data points that you got. And now we have 15 data points like that. And Then I'm gonna ask you to do linear regressions. And I think if I ask you to draw straight lines, which is to do the linear regressions, then most likely you guys gonna do that way. Even though you guys know the existence of two data points, which is like outliers. So in our like brain, if you think about yourself, say, okay, so somehow we plot them, and these data points, we kind of know that it's outliers. It's not the normal, it's abnormal. So you guys can kind of in your brain is intentionally is you're gonna remove that data points, and remaining certain data points you do the linear regressions, which is draw the straight lines. But the problem is the linear regressions is not gonna it's not gonna be done by you. It's supposed to done by computer. The information that the computers or is not gonna, there's no way they can see these figures. The information they have is like, remember 1 by 2. Now you have 15 data points. That's the only information, the numbers that the computer is supposed to see. And the biggest issue or challenge is that out of 13 data points, because the computer is not gonna plot, there's no way they can see which data points are outliers. There's no way. So assuming that situations, we don't know which data point is outlier. We don't know which data points that we're supposed to include, or we're supposed to exclude when you want to calculate the linear regression models. That's the problem. We don't know the existence of outliers at the first place. That's the problem. So let's try. Out of 15 data points, we have outliers, but the computer doesn't know. So since the computer doesn't know, I mean, the only thing is that we can do linear regressions in 2 norms and 1 norms. And I program it, and I ask the CVXPY to compute, and the compute the thetas and plot it. Interesting. In 2 norms, we got like that. In 1 norms, mean something weird. Do you guys can tell me why we got different regression outcomes or result out of it? When you do, if you think about these, so these are distance, say this is distance from 2. In the minimization process or the objective functions, you have to square it. That means if there's some outliers that the corresponding the discrepancy or errors are big, and you square them, so the negative effect gonna penalize a lot because we have squared. But on this side, we do have like that, but we're not gonna square it. That's why, I mean, that's I guess the kind of the reasoning behind. So the thing that you can learn from here is that you can use 1 norms or 2 norms. In most cases, it doesn't matter. You're gonna get the similar linear regression models out of it, which is good. But if you believe there's some lot of noises and outliers in your data set, probably one norm is gonna give us decent, right? So what I'm saying is that just try both and get the better one, better regression models out of it. Okay. And here, think about what makes difference. That's really important. It's really important to understand what makes them different. So we have to understand what kind of mechanism behind, and think about the definition of one norms and two norms and how much it penalizes it, like absolute values or squared. And that's gonna give us the big difference, especially when you have a lot of outliers.